Hey guys, welcome back to Vern's Valley with part two of chasing your first weather event this spring. Part one, we dove in of how just a general thunderstorm works, right? You need your dew point, you need a lifting mechanism, and you need some instability. Good juicy warm air. You need the dry air mass behind it, and then you need a low pressure system or something of that sort to make that lift, right? So this episode, we'll be going over skewed T-logs, some chase areas that I do, and kind of just a little more juice than the first one. So stick with me. Like, subscribe if you like what I'm doing here. Yeah, let's get to it. Hope I don't jaw jack too much, So, what is a skewed T-log? So basically, this is just a graph of the atmosphere. I'm starting at the surface, at the very bottom, and then obviously as you look up at the top of the chart, is very in the upper parts of the atmosphere. Obviously the green, red, you guys can read all that. Cape, if you guys remember, is how this is the measurement of how fast the air particle can rise in its environment. So more cape, the more robust, the more violent the updrafts will be. So basically that's what a skewed T-log is. This information is given from the National Weather Service, from the computer logs, and also on the day-to-day National Weather Service, does their balloons twice a day. But on the day of severe weather events, they do it quite a few times a day. I think it's every 3 hours, starting at like 6 a.m. So, for your new timers, gotta watch out for bust days. Basically, what a bust day is when the cap, there's a capping inversion. So there's warmer air higher up in the atmosphere, which will not allow the clouds or the moisture at the surface where we are to rise and create a thunderstorm. So a lot of times it'll be cooler, dry air where we are, like 60s, and then warmer up or higher up in the atmosphere, it'll be like 70 degrees. And then that air particle will rise, and that's how you get high elevated thunderstorm. So that only gets you rain and hail. It doesn't get you any of the good stuff, tornadoes. So more about bust days when you look at the skewed T-logs. You could look at the temperature. You can see the capping inversion. The temp and humidity are together at the surface, and as you go higher up, the temperature gets warmer, creating the capping inversion. So I correlated to a boiling pot of water with a lid on it. All that steam and energy is built up, and then when you release the lid, that's when the thunderstorm happens. So in order for that lid to break, you have to have daytime heating or a crazy amount of instability to create that lifting mechanism, or for that forcing to drive up that air particle to create the thunderstorm. So in the morning it rains, you have thunderstorms, warm front rolls through. It's 1 o'clock and you see the sun's breaking out. And that's where the sun starts to warm up the surface, and it creates that air particle warmer than anything around it, right? So that's where the cape becomes crazy in the afternoon. You could see these low hanging clouds. All those will come together eventually and conjoin and make a thunderstorm. So daytime heating happens 1 o'clock. For the next couple hours, the sun stays out. And then you look, the capping inversion is no longer there. That the temperature gradient comes out a little bit higher in the atmosphere, but you could see the cave values sneak right along it. So basically, that air particle sneaks right along that warmer pocket of air and continues going up, creating that updraft. So as you can see on the right side, warm moist air going up, and then on the left side, the cooler dry air pocket, as you can see, the humidity values is going down because warm dry air sinks. So you have those two forces fighting with each other, and then things get crazy. So like I said, the sun breaks out. the lid's off, and you can see all that steam release. That is the updraft, the thunderstorm being made. Those wind barbs on the right of the skewed T-log, like I said, this whole chart is based off of the bottom being the surface, the top being the upper part of the atmosphere. If you don't know how to read a wind barb, super easy. You guys can just, go look that up, and then come back when you obtain that knowledge. But basically in the surface, the winds start to the south, and then as you go up higher in the atmosphere, they crank out to the west. So in that, southwest, in this area, you have that rotation in that updraft. The LCL, as you can see here in green, and then the LFC in the in the yellow. The LCL is where the temperature and the dew point come the same, and that's where the clouds condense. So if you ever look up and you see a cloudy day, where that cloud base is, where it starts, that's where the temp and humidity are the same. So, and then that LFC is where that air partial, that cloud base, the condensation becomes buoyant and then starts to rise. So I'm still not sure how those two, they're the same. Still not sure how they're so different. Obviously you have the cloud base, and then where the LFC, obviously that's where the updraft starts. So is that the skinny disc that you see at the base of the storm? Pretty sure that's what it is, but not 100% sure. But basically here on the left-hand side, I wanted to correlate a picture I took. This was on I-35 a few years ago in Iowa, looking east. These storms were advancing towards Wisconsin. But basically I wanted to correlate the skewed T-log in a picture so you guys kind of get a better visualization of that. But you can see on the red, that's the storm side, and then I also highlighted the updraft, as you can see also in red on the left side with that picture. And then the purple, as you can see, is the EL, or the equilibrium point at which the parcel becomes cooler than its environment, so it can no longer rise, and that's where you get the anvil and the winds that high cranking that moisture out, creating that anvil. So you can see red, storm side, that's where everything's happening. And then on the left side is where I took the picture. That is dry, cooler air. That's after the storm passes. So like I said, again, I just want to show that so you guys can get a visualization. And then here you can see the LCL. Obviously that's where the cloud base starts. And then you can see where the red arrow goes up. That's where obviously your warm, moist air comes in, and then reaches that point where the updraft starts. And then obviously you have the cooler, drier air higher up fighting those two. As you can see, I illustrated there. They're not necessarily, the cooler air is not necessarily right there. Obviously it's probably where the rain and hail is, but I just wanted to show that those two forces fighting. So, and then you can see the rotating wall cloud where those, where that warm air starts to, go upward, and that cooler air kind of, fights with it. So that's where all the magic happens. So again, the 500 millibar winds, those really crank out the anvil. Probably placed to 500 millibar winds a little higher. Those might be 250 millibar winds, where the anvil is. And then 500 millibars were a little bit lower beneath the anvil. And then obviously the rain and hail is just below it, where that moisture can't go higher anymore, and then falls. And then obviously the arrows, warm moisture feeding into the storm. If ever storm is approaching and you feel cool air, the chance of a tornado, very slim. But if you have warm, moist air just ripping and roaring towards that storm, get some good hail, very good winds, maybe a tornado depending on the day. But yeah. But next topic I want to go over is my 3 areas to chase on a low pressure system. So these are very prominent in the springtime. You'll see a lot of these coming. But basically you have the warm front, the dry line, cold front, and then the triple point. Triple points where all of those meet. The low pressure center itself, you have the winds come from the south, and then they turn to the southeast, and those are just at the surface. And then you have the cooler, dry winds higher up, and then all those are crashing together. And that's where the triple point is, where all three of those intersect. So that's what the triple point is. And here is an example of a warm front. On the left-hand side, that is just a surface analysis with the winds. And if you guys again don't know how to read wind barbs, if you look to where the red is and the green, that's temp. Bottom is dew point. And then if you look in the middle of the wind barb, it's like a little white and a little black. That's partly cloudy, like sun's breaking out, a little bit of clouds. And then if you go to the west, the 73/66, that middle dot is all black, and that's cloudy. So, and then if you go to the north, you see the 58 degrees, 52 degrees. Obviously just below that, I have indicate where the warm front is. So if you ever see that surface analysis and you see the clouds breaking on that warm front, that's where I would go, because that's where you have the daytime heating breaking that cap, making it warmer on the surface to make those robust thunderstorms. And you just hope and pray that the thunderstorm stays on the warm front side. Don't want to suck in any of that cooler air. And the right-hand side is just a mesoscale description the National Weather Service puts out. Just wanted to show where the warm front sits on a low pressure system like that before they warn, give it a tornado watch, I should say. But and then again, like I described, trip point is where all three of them come together. They all intersect. This gets very messy, guys. Very rain wrapped. Things get hairy and scary. Okay. But if high risk, high reward, I would say people are gonna laugh. Whoever watches this who is a storm chaser, 80% of the time, I would say tornadoes happen there. Depending on the storm, depending on the setup, I go chase low or triple points. But like I said again, warm fronts can be very rewarding, but you just hope and pray that it stays on the warm, moist side of the boundary. And then obviously on the right, you see the mesoscale discussion. And then the dry line, cold front. Obviously that's where the very sharp gradient happens between like the 60s, 50s, dew points, the very rich environment, and then the very dry environment. And you have some very crazy instability there, right? Because you have those two forces absolutely colliding with each other. So those are very fun to chase. If the dew points stay good, there's enough moisture, everything stays together. Obviously, you can see here on the right, storms become easy. This was taken in Oklahoma like 5 years ago, but those storms were crazy down in Oklahoma and Texas. Something else down there. And here, another illustration of just the warm winds indicated in red going up higher up as the winds change to the west, gets cooler. You guys can pretty much look at that. Pretty much self-explanatory, But then here, I just wanted to correlate the low pressure system. So like I said, it's very prominent in the springtime. That's where you have, these big storms that ride the trough come in and they pull up the Gulf of America moisture, and then everything meets the dry air, the moist air, the warmer, cooler air, everything just, smashes. So when you have a prominent, mature supercell with a large tornado like this Mayfield one I have pictured, any tornado is a low pressure. It is a low pressure center. Okay. But when you have a very visualization of a supercell like this on radar, it's very easy to map out, from my standpoint, a low pressure system. So obviously you can see the L is a low pressure center itself. And then the red is a warm front on the front of the supercell, and then obviously the blue cold front, and obviously those two meeting up where the low pressure system, aka the tornado, is, and then obviously those warm winds feeding into it and then everything just wrapping together. So that's a low pressure center is a tornado. That's why your ears pop. That's why just a lot of things, crazy things happen. So here is again another, illustration depicting that. The forward flank downdraft is the underparts of the anvil. You have very high winds from the updraft, descending down, becoming the downdraft, obviously downdraft, hail, wind, excessive rains, flooding, and then you have a tornado behind it. So that's where a lot of shelf clouds happen, is the forward flank downdraft. That's where a lot of people get mistaken with tornadoes in the beginning of the storm because of that downburst of wind. But, the tornado is behind it. That's why a lot of cases, you see a tornado go through a town or somewhere, and then you go to the dam and you go assess, make sure everything's okay, and the sun comes out, and you're like, what? And that's because, that's the very back of it, So velocity, I'll just go over this very briefly. I'm pretty sure all you know what rotation is, but velocity is basically measured on the winds going away or towards the radar. So in this case, it's a screenshot from a tornado back in 2022 down in Gilmore, Iowa. This was a crazy day. Basically, the red indicates winds going towards radar, and then green's winds going away from radar. And then obviously you can see that velocity cup right there, the tornado on the ground. And then here, depending where you are and what radar you're using, the green and red will change. Green in this instance, winds going towards radar, red going away from radar. And then obviously you can see these two individual radar velocity couplets. Could those be twins? No one will ever know why we need storm chasers like myself to visually see the storm out in the field and to report back of what's actually happening. Otherwise, no one will ever know. And then weak rotation, hail core. This is a storm I was chasing, never produced anything. It was just very brief rotation, wasn't much. I just wanted to show that kind of just very weak. And then the little red and green spots, you might be like, is this all rotation? That's just hail. Very downpour, heavy downpours. Basically, the darker the color, the heavier the downpour, or heavier the hail, or stronger the winds. So again, 500 millibar winds. Like I said, this really cranks out the storm's upper parts of the atmosphere. The anvil really lifts the moisture away from the updraft. We really look for these troughs in the springtime. This is actually forecasted for Tuesday. I'm pretty sure I took this screen grab yesterday. But basically this trough comes in, very strong upper mid-level winds, and it ejects little impulse waves of these winds, so to speak. And then when those winds obviously meet up with the surface winds and that moisture, everything just becomes a war. So, like I said, these surface winds, 850 millibars. This is a little higher up than the surface. Surface about 950 millibars, 1,000. But basically, when these two winds collide, with the moisture, dry, warm, everything just, like I said, it's a war. But basically, I go on pivotal. I'm kind of transitioning to kind of what I look for in the springtime when I start chasing. I look for these sorts of things, the 500 millibar, the 850 millibar winds, especially the 850 millibar winds, because that carries the moisture. I mean, these are the two, or these are the actual true surface winds, but, the 850 millibar winds mean a lot to me. But basically, I look for low pressures. I look for the moisture. I don't care really about anything else because I have to have moisture. If there's no moisture, there ain't no storms. I worry about all other stuff later. So basically, I'll hop on Pivotal. I'll go to the GFS model, the Euro model. The Euro is more accurate. The GFS goes out a little bit more. You can correlate the two and kind of depict which one's throwing what changes when. But basically, I go through the whole 10-day outlook for the GFS, and then I think it's like 8 days for the Euro model. But I look for the moisture coming up, look for low pressure systems bringing the moisture up. And as soon as it's within reasonable driving range and it's starting to look good, that's what I look for. So basically, as you get closer to things, things become more accurate. You can start honing in on your chase day or requesting a day off or calling in sick, whatever you got to do. Red, obviously, warm, moist air coming from the Gulf of America, and then the cooler, dry air coming from the Dakotas, Canada, and obviously those two forces meet. Like I said, it's a war. I also use this as a tool. It's the Northern Illinois University, I'm pretty sure. If you guys go to my website, by the drop tab, I have the NIH models. This is what this is. So basically, they give a 1, 2, and 3 week outlook. So I just want to throw this on here so I look at. This is what a lot of storm chasers use, and you might see this floating around. I'm pretty sure this is AI generated, but obviously it's computer generated. I'm just not sure if it's AI generated or not. But basically, like I said, they do a week 1, week 2, week 3 outlook, and then so I go off that too, and then go off the pivotal and go off other things. So I just take a little chunk here, and be like, okay, here's kind of what it's looking like. Again, I go through the whole GFS. This was a screen grab, like I said yesterday. You can see here, moisture's finally being pulled to Minnesota, right? Dew points in the low 50s, mid 50s. That may get some thunderstorms, right? Nothing tornado crazy. It's a very large low pressure center low. So I'm like, all right, cool. Storms are starting to come up, right? Now this one was a couple days later. This is for like Sunday the 16th, the first today. It's 2 weeks away. No way that's right? I know. I'm crazy for even putting this on here, you're thinking. But like I said, this is where I look at. The models are starting to depict some storms coming into my area within the next couple weeks. So then I know I can start to get things ready within a couple weeks. Not saying it's going to happen, but that just gives me a timeline. So here you can see these are the surface winds where everything changes. For the low pressure center to the warm front. Basically, when the winds come from the south or the southeast, and then they change directly to the east, so to speak, that's where the warm front is. So where those surface winds change, you can also see on the temp graph as well, or the temp map, where those temps change, and then where the wind bars change, that's where the warm front is placed. So, like I said, all these things change. There's a screen grab from yesterday, okay? And then I look today, and there's not a storm in sight. There's no moisture within 3 states away. There's no low pressure system. There's no nothing. So it changes so fast with GFS, guys. That's why a lot of you will probably think I'm crazy for even talking about GFS. But like I said, these are the things I use and do. Why not share them? Because they might work for you. It might not. You might be like, this guy sucks. But you might be, I don't know, it might work out. Why not? Give it a try. We're very much scientists. You're basically just trying, you fail. You try again, fail. Try, fail again until it works. That's what a scientist is. So that's what we are. People are like, a scientist. Whatever. So anyways, guys, I hope you enjoyed the video. If you like what I do, please like, subscribe, comment, share it. Storm season is here, guys. Like I said, happy meteorological spring. My goal is to get everyone educated, get and learn before storm season hits, depending where you're at, and then we'll get some storm chase videos out, get some of those rolling. Hopefully, the goal this year is 15 tornadoes. So I want 5 of those to be photogenic, clear bases, to be absolute beauts, man. I can't wait. Be a good year, hopefully. With the grace of God, we'll get her done. So, real quick, guys. This year I'm going to be doing something a little different. Usually I don't like bringing people with me on storm chases, but feel by the greatness of my heart, I should start to spread my knowledge a little bit and bring people who maybe don't have the opportunity to go out chasing, or maybe who are too scared to go out for the first time. So, if you guys go to my website, go to scroll down and contact me. You just fill that out and then put in the message. I want to storm chase this year. Tell me where you're from. Kind of just give me a general background. You don't have to tell me too much. And then I'll get in contact with you, and then we'll kind of go from there. Like I said, depending where you live, depending where the chase day is. If you live in northern Minnesota and chase days in Iowa, we expect you to come to me, not me come to you. So whatever. So um, we'll do ride-alongs this year, and bring your cameras, bring snacks, bring money for gas. You don't have to pay for gas. I'd like as much help as appreciated. But just bring snacks, cameras, chargers, got all sorts of stuff. Bring some shovels just in case you get stuck on a middle maintenance road that I don't know about. But yeah, like I said, guys, stay tuned for part 3. We're going to be diving in, be a little deeper, talk about more of the photograph side, we'll go more in depth to the skew T-logs. We'll go more into the soundings, and you click on models on the GFS. So stay tuned, guys. I hope you enjoy your first couple weeks of March, and stay safe out there for the folks down in Alabama, Mississippi, all those good people down there for Tuesday and Wednesday's event. So stay tuned, guys.